At the end of the 19th century, physics appeared to be nearly complete. The laws of motion were understood, electricity and magnetism had been unified, and the behavior of heat and energy seemed explainable through established principles. Many scientists believed that only small details remained to be filled in, that the structure of the physical world had already been mapped out. But beneath this confidence, there was a quiet problem that refused to disappear. It came from something as ordinary as heat. When objects are heated, they emit radiation, a glow that changes color as temperature increases. This phenomenon, known as blackbody radiation, had been studied extensively, yet the existing theories could not fully explain the observed results. At certain wavelengths, classical physics predicted an infinite amount of energy, a conclusion that clearly did not match reality. This contradiction became known as the ultraviolet catastrophe, a sign that something fundamental was missing. It was in trying to solve this problem that Max Planck made a decision that would change physics forever. Max Planck was born in 1858 in Germany, into a family deeply connected to education and intellectual life. From an early age, he showed a strong interest in science, particularly in the laws that govern energy and thermodynamics. Unlike some scientists who were drawn to dramatic breakthroughs, Planck was methodical, disciplined, and cautious. He believed in the consistency of physical laws and approached problems with patience and precision. His early career reflected this mindset. Planck focused on thermodynamics, the study of heat and energy, and worked to understand how energy is transferred and transformed. He was not initially trying to overturn existing theories. In fact, he believed that classical physics was fundamentally correct. His goal was to refine it, to resolve its remaining inconsistencies without abandoning its core principles. The problem of blackbody radiation drew his attention because it sat at the intersection of theory and experiment. Experimental data showed a clear pattern of how radiation was distributed across different wavelengths at various temperatures. However, theoretical models could not reproduce these results accurately. The equations either worked at low frequencies or high frequencies, but not both. No single explanation could account for the full range of observations. Planck approached this problem with determination. He worked through the mathematics, testing different assumptions, trying to find a way to align theory with experiment. For a long time, progress was slow. The existing framework simply did not allow for a consistent solution. The more he examined the problem, the clearer it became that a fundamental change might be required. In 1900, Planck made a move that he himself initially viewed as a mathematical trick rather than a physical truth. He proposed that energy is not emitted or absorbed continuously, but in discrete units, which he called quanta. Instead of energy flowing smoothly, it would come in small packets, each proportional to the frequency of radiation. This idea allowed him to derive an equation that matched the experimental data perfectly. It solved the problem. The distribution of blackbody radiation could now be explained without leading to the ultraviolet catastrophe. The results were accurate, consistent, and aligned with observation. Yet the assumption behind them was deeply unconventional. Energy, which had always been treated as continuous, was now being described as discrete. At first, Planck himself was uncertain about the meaning of this idea. He saw it as a necessary step to make the mathematics work, not as a description of reality. But the implications were too significant to ignore. If energy is quantized, then the foundations of physics are different from what had been assumed for centuries. This marked the beginning of quantum theory, although Planck did not fully develop the theory himself. His introduction of the quantum concept opened the door to a completely new way of understanding the physical world. It suggested that at very small scales, nature does not behave in a continuous and predictable manner, but in discrete steps governed by probabilities and interactions that defy classical intuition. The importance of this shift cannot be overstated. It challenged the idea that physical processes could be described entirely by smooth, continuous equations. It introduced a level of discontinuity into the heart of physics, forcing scientists to rethink their assumptions about energy, matter, and the nature of reality itself. At the time, however, the full impact of Planck's work was not immediately recognized. Many scientists viewed the quantum hypothesis with skepticism, seeing it as a useful tool, but not necessarily a reflection of physical truth. Even Planck approached it cautiously, continuing to work within the broader framework of classical physics. Yet the idea had been introduced. A small change in assumption, made to solve a specific problem, had created a path that would lead to one of the most profound transformations in science. And Max Planck, through careful reasoning and persistence, had become the starting point of that transformation. After Max Planck introduced the idea that energy is emitted in discrete units, the scientific world did not immediately shift to accept it. In fact, for several years, the concept of quanta remained uncertain, almost uncomfortable, even to Planck himself. It solved the problem of blackbody radiation with precision, yet it did so by challenging one of the most deeply rooted assumptions in physics, the belief that energy flows continuously. Planck did not initially see himself as a revolutionary. He believed that the foundations of classical physics were still valid and hoped that his quantum idea would eventually be reconciled within that framework. To him, quantization was a necessary step to make the equations match reality, not a declaration that the nature of energy itself had fundamentally changed. This cautious interpretation slowed the immediate acceptance of his work, but it also reflected the magnitude of what he had uncovered. The turning point came when other scientists began to explore the implications of his idea. Among them was Albert Einstein, who in 1905 took Planck's concept further than Planck himself had intended. Einstein proposed that light itself could be understood as being made up of discrete packets of energy, later called photons. This was not just a mathematical assumption. It was a direct claim about the nature of light. Einstein used this idea to explain the photoelectric effect. In this phenomenon, light shining on a metal surface can cause electrons to be ejected, but only if the light has a certain minimum frequency. Classical wave theory could not fully explain why intensity alone was not enough. Einstein's quantum interpretation provided a clear answer. Light transfers energy in packets, and only packets with sufficient energy can release electrons. This marked a critical shift. Planck's quantum idea was no longer just a mathematical tool. It was becoming a physical reality, something that described how nature actually behaves. The concept of quantization began to spread beyond radiation into other areas of physics, gradually building a new framework. Planck observed these developments with interest, but also with a degree of caution. He recognized the importance of the work, yet he remained measured in his conclusions. His approach to science was deeply rooted in stability and consistency. He was not driven by the desire to overturn existing systems, but by the need to understand them as accurately as possible. Even as quantum theory began to grow, Planck maintained a balance between accepting new ideas and preserving what still worked within classical physics. At the same time, experimental evidence continued to support the emerging quantum perspective. Studies of atomic spectra, the specific wavelengths of light emitted by atoms, revealed patterns that could not be explained by classical models. Electrons appeared to occupy discrete energy levels, moving between them in ways that produced quantized emissions of light. These observations aligned naturally with the idea that energy exists in discrete units. This growing body of evidence strengthened the case for quantum theory. What had begun as a solution to a single problem was now expanding into a broader explanation of atomic behavior. The structure of atoms, the emission and absorption of radiation, and the interaction of matter with light all began to fit within a quantum framework. Planck's role in this transformation remained foundational. Although others extended and developed the theory, his original insight provided the starting point. Without the introduction of energy quanta, these later advances would not have had a basis to build upon. His work had opened a path that others would follow, often in directions he himself had not anticipated. In recognition of his contribution, Planck was awarded the Nobel Prize in Physics in 1918. This acknowledgement came at a time when the importance of quantum theory was becoming increasingly clear. The scientific community had begun to accept that the classical description of nature was incomplete and that a new set of principles was needed to describe the behavior of matter and energy at small scales. Yet, even with this recognition, the transition was not simple. Quantum theory introduced ideas that were difficult to reconcile with everyday experience. The notion that energy is quantized, that particles can behave like waves, and that outcomes can be probabilistic rather than certain challenged the intuitive understanding of the physical world. These concepts required a new way of thinking, one that would take time to develop fully. Planck remained a steady presence during this period of change. He supported the development of quantum theory while maintaining a commitment to clarity and logical consistency. He engaged with other leading scientists, helping to guide discussions and encourage further exploration. His role was not only that of a discoverer, but also of a stabilizing figure within a rapidly evolving field. At the same time, his influence extended beyond his own research. Planck played an important role in the German scientific community, holding positions that allowed him to support other researchers and promote scientific work. He recognized the importance of collaboration and communication, understanding that major advances often come from collective effort rather than individual achievement alone. As quantum theory continued to develop, new figures such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger would build on the foundations laid by Planck. They would introduce models and equations that described atomic and subatomic behavior in greater detail, creating a comprehensive framework that could explain a wide range of phenomena. These developments would eventually form the core of modern quantum mechanics. Through all of this, Planck's original idea remained central. The concept that energy is not continuous but comes in discrete units became one of the defining principles of modern physics. It reshaped the understanding of nature at its most fundamental level, influencing everything from atomic structure to the behavior of light. What had begun as an attempt to resolve a specific inconsistency had grown into a transformation of the entire field. And at the center of that transformation was Max Planck, whose careful reasoning and willingness to consider an unconventional solution had opened the door to a new understanding of reality. As quantum theory continued to take shape in the early 20th century, the scientific world entered a period of rapid and often unsettling change. The ideas that had begun with Max Planck's simple assumption about energy quanta were now expanding into a full framework that challenged nearly every classical intuition about how the universe operates. Concepts such as uncertainty, probability, and wave-particle duality began to replace the older, more deterministic view of nature. At the center of this transformation, even as others pushed the theory forward, Planck remained a steady and influential presence. What made this period remarkable was not just the speed of discovery, but the depth of its implications. Physics was no longer describing a world that behaved in smooth, predictable ways. Instead, at the smallest scales, nature appeared fragmented and discontinuous. Electrons did not move in clearly defined paths like planets around the sun. Instead, their behavior could only be described in terms of probabilities. Energy did not flow freely in all amounts, but in fixed packets. These ideas required scientists to rethink the very meaning of physical reality. Planck, who had introduced the first step into this new world, watched as the theory evolved far beyond its original form. He maintained respect for the younger generation of physicists who were developing quantum mechanics, including figures like Heisenberg and Schrödinger. Their work introduced mathematical systems capable of describing atomic behavior with extraordinary accuracy. Yet at the same time, Planck was not entirely comfortable with the philosophical implications of these developments. His scientific instincts had been shaped by a belief in order and continuity. The idea that nature might be fundamentally probabilistic rather than deterministic was difficult to fully accept. While he supported the use of quantum theory as a practical tool, he remained cautious about its deeper interpretation. This tension reflected a broader divide within the scientific community, where some embraced the new ideas fully, while others questioned what they implied about reality. Despite these philosophical challenges, the success of quantum mechanics could not be ignored. It provided precise explanations for atomic spectra, chemical bonding, and the behavior of particles at very small scales. Experiments repeatedly confirmed its predictions, strengthening its position as the most accurate description of the microscopic world. The theory that had begun with Planck's work was now central to physics. During this time, Planck's role extended beyond research. He became one of the leading figures in German science, holding positions that allowed him to influence the direction of research and support the scientific community. He was respected not only for his discoveries, but also for his integrity and commitment to the advancement of knowledge. His presence provided continuity during a period of rapid change. However, the environment in which he worked was becoming increasingly difficult. The political situation in Germany was shifting, and the rise of the Nazi regime in the 1930s created serious challenges for scientists, particularly those of Jewish background. Many leading physicists were forced to leave the country, resulting in a significant loss of intellectual talent. Planck, who was deeply committed to German science, found himself in a complex and often troubling position. He attempted to navigate this situation with caution. Planck did not openly support the regime, but he also chose to remain in Germany, hoping to preserve what he could of the scientific community. He used his influence to advocate for colleagues and to maintain academic standards where possible. This was not an easy task, as political pressures increasingly interfered with scientific work. The personal cost of this period was significant. Planck faced not only professional challenges, but also personal tragedy. His family was deeply affected by the events of the time, and he endured losses that reflected the broader turmoil of the era. These experiences added a human dimension to his life, showing that even those at the forefront of scientific achievement are not separate from the events of history. Despite these difficulties, Planck continued to represent a commitment to science as a pursuit of truth. He believed that scientific knowledge transcends political systems, that it belongs to humanity as a whole rather than to any single nation or ideology. This belief guided his actions, even in a time when the independence of science was under threat. As the world moved toward the Second World War, the scientific landscape continued to evolve. Quantum theory expanded into new areas, influencing fields such as solid-state physics, nuclear physics, and eventually the development of technologies that would shape modern life. The principles that had emerged from Planck's original idea were now being applied in ways that extended far beyond their initial context. Through all of this, Planck's contribution remained at the core. The concept of quantization, simple in its formulation yet profound in its consequences, continued to underpin the entire structure of modern physics. It provided the starting point from which more complex theories could develop, anchoring a field that would otherwise have no foundation. His legacy during this period was not defined by constant new discoveries, but by the enduring importance of his original insight. He had introduced a principle that could not be undone, one that forced science to move in a new direction. Even as others expanded and refined the theory, the initial step remained his. By the time the world entered the mid-20th century, the transformation of physics was complete. The classical view of a continuous, predictable universe had been replaced by a quantum view, where uncertainty, probability, and discrete interactions defined reality at its most fundamental level. And at the origin of that transformation stood Max Planck, whose careful attempt to solve a single problem had reshaped the entire understanding of the physical world. As Max Planck moved into the final years of his life, the scientific revolution he had unintentionally begun was no longer a theory in development, but a fully established foundation of modern physics. Quantum mechanics had taken form through the work of multiple scientists, and its principles were now being applied across disciplines. What had started as a solution to a narrow problem in blackbody radiation had expanded into a framework that defined how matter and energy behave at the most fundamental level. Planck, who had once viewed his quantum hypothesis as a temporary mathematical step, now witnessed its complete transformation into a new vision of reality. The world of physics had changed permanently. Atoms were no longer imagined as simple systems with predictable behavior. Instead, they were governed by probabilities, discrete transitions, and interactions that could only be described through complex mathematical models. The certainty that had once defined classical physics gave way to a more nuanced understanding, where outcomes could be calculated but not always predicted with absolute precision. Despite the unfamiliar nature of these ideas, their success was undeniable. Quantum mechanics explained phenomena that classical physics could not, from the stability of atoms to the emission of light and the behavior of electrons and materials. It became the foundation for entire fields of research, influencing chemistry, electronics, and later technologies that would define the modern world. Planck's role in this transformation remained unique. He was not the one who developed the full structure of quantum mechanics, but he was the one who opened the door. His introduction of the quantum concept provided the first break from classical thinking, creating the space in which new ideas could emerge. Without that initial step, the developments that followed would not have been possible. At the same time, the world around him was undergoing profound change. The political and social upheavals of the early 20th century had a direct impact on the scientific community. Many of Planck's colleagues had left Germany, and the intellectual environment that had once supported rapid progress was deeply affected. Planck himself endured significant personal loss during this period, including the death of family members, experiences that reflected the broader tragedies of the time. Through these challenges, he maintained a commitment to science. He believed that the pursuit of knowledge should remain independent of political forces, even when circumstances made this difficult. His dedication to preserving scientific integrity during a turbulent era became an important part of his legacy, showing that the value of knowledge extends beyond immediate conditions. In his later years, Planck became a symbol of continuity. He represented a link between the classical world of 19th century physics and the modern quantum era. His career spanned a period of transformation unlike any before it, and his work provided the starting point for that change. Younger scientists, building on his ideas, carried the field forward, but they did so within a framework he had helped establish. Max Planck died in 1947. By that time, the world had entered a new scientific age. The principles of quantum theory were being applied in ways that would soon lead to technologies such as semiconductors, lasers, and advanced materials. Although these developments came after his lifetime, they were direct consequences of the shift he had initiated. His influence continues to be felt in the present. Modern physics, chemistry, and engineering all rely on quantum principles. The devices that power communication, computation, and energy systems depend on an understanding of how electrons behave within materials, knowledge that is rooted in quantum mechanics. Even the study of the universe at its largest scales connects back to the behavior of particles at the smallest scales. What makes Planck's story especially powerful is the nature of his discovery. He was not seeking to overturn physics. He was trying to solve a specific problem, to bring theory into agreement with experiment. Yet in doing so, he uncovered a principle that required a complete rethinking of the foundations of science. This reflects a broader pattern, where major breakthroughs often arise from focused efforts rather than deliberate attempts to create revolution. His work also highlights the importance of persistence. The problem of blackbody radiation was not solved quickly. It required careful analysis, repeated attempts, and a willingness to consider ideas that did not fit within existing frameworks. Planck's ability to continue working through these challenges, even when the solutions seemed uncertain, was central to his success. Looking back, his contribution can be seen as both simple and profound. The idea that energy is quantized can be stated in a single sentence, yet its implications extend across all of modern science. It changes how we understand light, matter, and the interactions that define the physical world. It reveals that at the deepest level, nature does not behave in a smooth and continuous way, but in discrete steps governed by fundamental principles. This insight reshaped not only physics, but the entire scientific worldview. From the behavior of atoms to the technologies that define contemporary life, the influence of Planck's work continues to expand. It serves as a reminder that even the most established systems of knowledge can be transformed by a single, well-reasoned idea. And in that transformation, Max Planck's legacy remains clear. He did not simply contribute to science. He changed its direction, opening a path that continues to guide our understanding of reality at its most fundamental level.